We're going to learn how to attack some slightly more difficult inductive proofs. So these are using proof by mathematical induction, and these focus on divisibility. So I'm assuming here that you're familiar with divisibility and you're familiar with proof by induction. This is not an introductory video. So moving through our proof, we've got to prove that 2 to the 2n minus 3 times n minus 1 is always divisible by 3. So we go for our base case. Base case n equals 1. So on the left hand side we've got 2 squared minus 3 by 1 minus 1. That's 4 minus 3 minus 1 is 0, which is, so that is divisible by 3. Okay, 0 is divisible by, so the base case holds. So we assume, for the inductive hypothesis, we assume it's true, the proposition is true for n equals k. That would give us 2 to the 2k minus 3 by k minus 1. Now assume it's true. What's true? Divisible by 3. So we're going to call that 3a, where a is some positive integer. Alright, so remember 3 times an integer, and we're dealing with positives because we're doing proof by inductions, and n is greater than 1 or greater. Okay, so that means we're dealing with positive integers here. Now I know I'm going to use that later on, so I'm going to just mark that in there as 1. So we can refer back to that later on. Now for the inductive step, by substitution we have 2 to the 2 outside of k plus 1 minus 3 times k plus 1 minus 1. Now that would lead from the inductive hypothesis, and so that would be divisible by 3 too if that were true. We'll call that 3b, where b's a positive integer. Now when we say left hand side here, we mean the stuff that you might see in that faint pink color, and what we have here is some index laws, so, and also some distributive rule as well. So we would have essentially 2 to the 2k plus 2, 3k minus 3 minus 1, which is 2 to the 2k times 2 to the 2, index law 1, and we have 3 minus 3k minus 4. Now there is a factor of 4 present, and I've swapped the last 2 terms on the previous line there. So pause the video at any stage if you need to see where that went. We have a factor of 4. Now for the bit that requires a fair bit of initiative and insight initially, going back to line 1 there, that was what 3a equals. Looking at that, we have something close there. We have the same, except for we have to add 3k on. So that's forgivably, initially, that is a tough step to see, but that's why we practice these to become familiar. So what we have is actually 3a in the brackets there, but we've had to add 3k on there. So we have 3a plus 3k in the brackets. We still have minus 3k on the outside. So we've used 1 there. Now we can go further. We can expand and do a few things here. You have a look. So we have 12a plus 9k there. We have a factor of 3, so we have 3 outside of 4a plus 3k. So we have 4a plus 3k is an integer. So that's the same as saying 3 times b above. Okay, so because these are both integers, 4a plus 3k and 3b from above, they're integers, so they're equivalent statements. So that equals the right hand side. So it's true for k plus 1. Therefore, by the process of induction, it's true for the base case when we assume n equals k. It is also true for n equals k plus 1. So by induction, it's true. Okay, QED.